Hello, good evening. Welcome to Davidson College, and I'm glad that you're here for tonight's Smith Lecture. To begin, I'm going to introduce myself. My name is Anthony Kuchera. I'm an associate professor in physics here at Davidson College. And before we begin, I want to acknowledge a few people and organizations that made this possible. So to begin, the Public Lectures Committee, John Wertheimer, Alexis Yates, Debbie Booth, members of the physics department, such as Mario Bologna, for inviting, organizing, and scheduling the events for Dr. Alexander's visit today. I want to give a little history behind this lectureship. So the Henry Louis Smith Lectureship was begun by gifts from Julia and Helen Smith in memory of their father, an 1881 graduate of Davidson College. The lectureship recognizes Dr. Smith's important contribution to education and to the advancement of his alma mater as a professor of physics and astronomy from 1887 to 1901, and as president from 1901 to 1912. It is the wish of the donors that these lectures reflect Dr. Smith's abiding interest in the expansion of knowledge in every scientific field and its implications for current and future living. It is hoped that distinguished scholars and researchers, those of recognized ability and significant contribution, and those on the cutting edge of new scientific developments may be brought to the Davidson campus to present these lectures. The lectureship is intended to carry forward both in time and in scope the interest in science for which Dr. Smith was known, and to encourage Davidson College's efforts toward more closely involving the traditional liberal arts with scientific advances in research. So with those criteria, tonight's speaker, I think, hits all of those. And so I'd like to begin by introducing Dr. Stephen Alexander. So he's a professor of physics at Brown University. He's a theoretical physicist specializing in cosmology, particle physics, and quantum gravity with over 100 publications in these fields. He got his Bachelor of Science degree in Haverford College, then went on to a PhD from Brown University and had postdoctoral positions at Imperial College London and the Stanford Linear Accelerator Center. Throughout his career, he's been presented with numerous awards, too many to say all here at once. I'll just highlight a few of these, such as the National Geographic Emerging Explorers Award, the AAAS Powell Memorial Award, the APS Boucher Award, the Isaac Asimov Science Award, and he's also a fellow of the American Physical Society. Dr. Alexander has served as the president of the National Society of Black Physicists, and he's also been featured in popular media outlets such as NPR and Forbes magazine. He's the author of 2 books, one titled Fear of a Black Universe, An Outsider's Guide to the Future of Physics. But in addition to that, he's also an accomplished jazz saxophonist, as you might be able to see here if you're able to see, who has performed and recorded with many prominent musicians. Okay. In addition, something that he's very proud of is he founded a nonprofit called Sound Plus Science. This is a nonprofit to empower underestimated youth and provide them with new career pathways into the world of STEM. So he's the author of a book called The Jazz of Physics, which happens to be the title of tonight's lecture. And so with that, please help me welcome Dr. Stephan Alexander.
Can somebody help me find Stephan Alexander? I mean, who's this guy? I mean, I'm listening to it like, that's not me. Trust me. I'm like, no. And I hope that it's some kind of inspiration for students of Davidson College, which is even an idiot like me can do it. Okay. I think I spoke to some of the students, a lot of students, which was probably the biggest joy of being here, because I went to Haverford College, which is a very similar, now that I've been to Davidson, and that's why I came to Davidson, because I love small, like, top-notch liberal arts colleges. That's why I went to Haverford, right? And and let's say I'm really, the word impress is like kind of like, when something is like cliche. Thank you. I'm sometimes bad with words. Kind of cliche. But I was impressed. I am impressed. And I think really Davidson, the legacy of Dr. Smith really speaks loud here, which is why I'm going to give the talk I'm going to give. because y'all are smart and I'm gonna nerd out a little bit here. But you know, one of the things that impressed me about Dr. Smith, after given the enthusiasm that the physics department has for him, because one of the things that I got to do after lunch was go and check out his X-ray stuff that's so proudly profiled in the physics department, was also that he was a high school principal. Before, you know, becoming this lofty president and professor, he went back and served the community, and that explains why Davidson, his legacy is such a strong teaching scholarship university. College, my apologies. You know, we mix those things up a lot. So it's a real honor. It truly is a real honor to be here in service to his great legacy, and I really appreciate it. Thank you so much. So on that note, I'm a nerd out. So yeah, the Jazz of Physics. I was trying to give a different type of title, but it is what it is. Let's begin. This is actually a picture, and I give similar talks like this, and I didn't realize that actually is a picture of me, and I didn't even know that. I thought it was a picture of some like famous jazz musician. It's actually me, and you could tell because I didn't button my shirt, and like so that's me. And this really begins with I'm really sort of targeting my talk towards the young people in the audience, okay? Which was that as a younger person, I remember liking music and being an inquisitive person growing up in the Bronx, New York, and this is in the 80s. And it was, you know, back then, I'm gonna be real and frank with y'all. Back then, there were the people that were successful in my neighborhood were not scientists, because there were none. Okay, I mean, the successful people were other people. Okay, let's say they were doing things up the hill from where I lived, and one of the pathways to success is to be a musician. Where I grew up, and I grew up in a musical family, and it was expected of me to be a musician. But I was also kind of inquisitive, and I discovered through a high school teacher, Mr. Daniel Kaplan, in my high school, DeWitt Clinton High School in the Bronx, that he was our physics teacher, but he was also a jazz musician, because he had to pay the bills. So the way to pay the bills as a working jazz musician in New York was he became a teacher, and then he played gigs at night. Okay, so because of this, my 15-year-old self, when he taught physics in my sophomore year, he took me into his little office and said, listen, kid, I know you're gonna cut class, okay? But here's what you're gonna do. You can always come hang out in my office. We got music to listen to, we got this, we got that. And oh, by the way, there's this book about Albert Einstein you could read about. And it was because of that teacher that really got me thinking about the possibility of becoming a scientist. But one of the things I struggled with, right, I had this idea that maybe I'm not good enough to be a scientist. I didn't fit the bill of being a scientist. Did I fit the bill of being a musician? And that struggle happened with me in terms of my identity. Where did I fit in? So what I'm going to be talking about here is a reconciliation, a way that I reconcile those things. And I was talking to some colleagues here at Davidson, I'm not going to point some people out, who actually have had similar journeys that I have. So what I'm talking about here is nothing new. And in fact, we all have our own journey in this way, trying to come to terms with our identity, who we are, and rather than what society or other people impose on us. So this is kind of that journey. Am I a scientist? Am I a musician? Am I neither? Am I both? Am I good enough? These internal voices. So I want to kind of talk about certain people that kind of entered into my life, not personally. I mean, these people were not alive when they entered my life, maybe in some imaginary life, that inspired me to make me feel like, oh, well, maybe it's kind of okay to like science and music and not have to choose between one or the other. The first one was John Coltrane. So John Coltrane, how many of y'all, I'm gonna get embarrassed. Obviously, he's an American legend. And he did so much. They once asked a bunch of radio personalities to vote the top album of the century, and it was like 90-something%. I mean, we're talking about rock musician and all kind of stuff. They voted "A Love Supreme" to be the album of the century, and that was the album that one of his great albums. But another thing about Coltrane that I learned was that he didn't stop with just being a great musician. He wanted to push his music to new heights, and as a result, he went after other sources, including a study of Albert Einstein. And so this is his hand-drawn picture that my book begins with. And my book is an interrogation of what's sort of like a detective story to figure out what's behind this. Because this was not known to people in the jazz world. And if there's time, I'll get back to this diagram. But here is the person who is, I'm fully aware, I know, and I have some jealousy here. I got some, that Steph Curry went to Davidson, and I am like, why didn't he come to Harvard? Well, we have a Division III basketball player. Okay, fine, okay, I get it. But the point here is that, in the world of jazz, Coltrane is it. Train is it. So then for Train to say, I'm gonna go study some Einstein, then you got to pay attention, right? The problem is that we never learned that. So I learned that later on by talking to his son, Ravi Coltrane, and talking to Yusef Lateef and Sonny Rollins when I was writing my book. And they revealed that Coltrane was a physics nut. Anything he got his hands on about Einstein, he was reading it. And so this diagram seems to reflect some of this. Of course, another person that was influential was Albert Einstein, because Einstein said that if I wasn't going to become a physicist, I would have become a musician, because I think in terms of music. I dream in terms of music. He wasn't like some virtuoso on his violin, but he was actually by some great violinist known for his tone. Okay, so he had a great sound. And I was talking to our colleague here, raising his hand there, who is also viola and violinist. And he says that one of the things that is important in playing the violin or the viola is your sound. So Einstein was known for his sound. But Einstein, when he would get stuck on a physics problem, he would actually go off to a piano, which he didn't know how to play, and improvise until some new idea came to him. So obviously, what is Einstein and Coltrane? What do they have to do with each other? And that's what we're going to talk about today. The end of the reconciliation, I had to, sort of figure out in my journey towards becoming a professional scientist and using my music as a way to keep me sane, okay? So I spoke to a bunch of students this morning, and I was just expressing, these were like students in a intro astro class that non-physics majors take, which is a wonderful class. It's a long class, I must say, and the students were well awake, and they were doing somersaults. It was amazing. And I was talking about, I forgot what I was talking about. I was talking about how it is, why it is I stayed in music while I was pursuing a path as a physicist. And the reason why is that a lot of my music friends served as a community for me, because they love when I was nerding out about my science, the musicians. Oh yeah, tell me about this Einstein's relativity, man. I want to play that. I'm like, oh, sure, I'll tell you. Can you show me how to play that scale? So there were things like there were soundboards for me. Like, musicians are nerds, okay? They're not the cool people you think that are hanging out there on the stage and paparazzi and all that stuff. I got to hang out with some of them. And maybe I'll come back to that in a second. But it turns out that the real rock star here is Pythagoras. That this reconciliation, me trying to, connect my music with my science, Am I a musician? Am I a scientist? Am I neither? There's nothing new. It's just that I didn't learn that in college. I wish I would have learned that. It started back in roughly 500 BC at the birth of what we call Western science. The Pythagoreans, the birth of Western science coexisted with the birth of what we now call tonal Western music. Now, I use the word Western because actually nothing really is Western. A lot of these ideas were borrowed. Pythagoras was, the legend had that he spent 18 years in Egypt in these mystery schools, right? And a lot of the themes I'm talking about here actually existed in other parts of the world. But I need to kind of, commit myself to something. Otherwise, it becomes a year-long course that I did teach at Dartmouth with a historian of science, Richard Kramer. So I'm kind of compressing a lot of this information in a couple of slides. So what did Pythagoras discover? Now this is, we're gonna have to, I just want to get my water. Thank you so much. So what Pythagoras believed is this idea called music of the spheres. So back in those days, they wanted to understand, philosophers wanted to understand the motion of the planets. No one understood, usually that idea of how the planets are moving in the night sky were usually ascribed to some kind of demigod that's making these things move. But the Pythagoreans believed that you can come up with a mechanism, a way to understand this. And Pythagoras' idea was that it had to do with harmony. That the planets, as they were moving around, were playing a harmony, literally they were playing music, okay? In correspondence to number. So there's this Pythagorean idea that all is number. So 1, 2, 3, 4, you can think about 1 and 2 and 3 and 4 corresponded to different orbital distances. And as a planet moved around a circle, they were playing this harmony. Obviously, that sounds like madness. And nobody could hear these planets, but he somehow had this mystical capacity to understand this. So he decided to experiment with this, and he built an instrument that would actually prove that this was actually happening. And that instrument is called a monochord. It's basically an old-fashioned guitar, right? Except it's a guitar at one string. So here's a monochord. There's a string, and you see that thing in the middle here? And you could slide it back and forth. And he discovered something interesting. And I'm going to demonstrate that with my set with this little toy here, $10,000 toy. I like to, because people think this is a toy, it's not serious. And so, to the picture here, at the top, that corresponds to the lowest tone. If I close all the holes here, right, then a wave will set up in here. And if I play that, okay. Now, what he did then with this thing is that he went to 1/2. That's the other integer. Remember I said 1 and 2. He's trying to do harmony in spirit. That becomes and 1/3. Anybody can guess? Right? That's a perfect fifth. In music theory, we call it the dominant. Very important in music harmony. And of course, the fourth is 2001: A Space Odyssey. Okay, so what Pythagoras discovered in terms of understanding this music of the spheres idea, which is not confirmed, is what we call this. That's our Western musical scale. So Pythagoras didn't only discover the Pythagorean theorem, but actually our Western musical system. All right. So but here's the thing that was funny. We got then all that music stuff came out of this. But whatever happened to understand the motions of the planet? It took 2,500 years after Pythagoras and his followers, including Plato, Aristotle, Ptolemy, and a whole list of other people, to try to work with this Pythagorean idea, which went from numbers to geometry. So Plato took the system of numbers of Pythagoras and turned it into a system of perfect spheres, that the planets are moving around in perfect spheres. And of course, Ptolemy took this idea of the epicycles, more and more spheres. The model got more and more complicated, and it just didn't work. The Arabs, basically, who were the inventors of algebra, actually did get the model to work. They wrote a book called The Alchemist, and this book is like, it's a tour de force, okay, of how to make a very complicated model that was wrong work. But then comes on the scene this individual in the 1600s, who had a very interesting life. He rose to such prominence in Germany, even though apparently he took only 3 showers in his entire lifetime, that he had a very difficult life, but he was able to get his mother forgiven to be burned at a witch trial, even though he didn't really get along with her. He was an interesting character. And to make a long story short, he tried to figure out the same problem. Why the planets move, what's causing the planets to move around? And he had some ideas, and they all were wrong. He did that for about 2 decades of his life. And then he was following Plato. And when he realized that Plato had this idea of these, Platonic solids, and he tried to make it work with that, he realized that Plato was a follower of Pythagoras. And that this actually, it's not about geometry, it's about music. So this is his handwriting there. And what he did was he took the data of the planets that was known at the time from his boss, Tycho Brahe, who got his nose sliced off in a sword duel. He has a metallic nose if you look it up online. Interesting character too. And what he did was, very simply, they had information about how fast the planet was going around the sun. And he said, well, let's do what Pythagoras wanted to do. Let's assign a ratio, fastest and slowest for every planet, and create a ratio, right? And write down a musical note for that. And so what he did was he found and he wrote down all those notes, trying to see whether or not there's a pattern there. There's a music of the spheres. Now, he was quite a religious person too. He was a tremendous mind. Clearly a tremendous, we call him the first astrophysicist, the first person to write down equations for astrophysical phenomenon. That's why we have satellites called the Kepler satellite today. But his way into this was to actually use music to understand this. And he found nothing. He found cacophony. He found dissonance. He did not find the music of the spheres. But he didn't give up. He so believed that there was some demigod sitting at the center of the sun enjoying the music of the spheres as the planets were going around. He wanted to find that music. He was going after the perfect fifth, the ratio 2/3. This 2/3 ratio, the third one there. Okay? And he found it, but he didn't find it with the individual planets. He found it with all the planets. He found it with polyphony, all the notes at the same time. And that equation is the period, the length that it takes a planet squared to the square power is equal to the distance to the sun when the planet's close to the sun to the cube power. And that is the equation of the elliptical orbit. So he found the perfect fifth in an equation, and he wrote this equation down. And that equation was able to explain every single planetary motion in our solar system, and now today, billions of planets outside of our solar system that's been discovered by the Kepler satellite. Fast forward a few decades later, Isaac Newton said, why does Kepler's law work so well? And that allowed him and Leibniz to invent calculus to understand now the force of gravity. Then that leads out to our modern era, Albert Einstein. So the point here is that I wish I would have learned this as a student, that music and science were interlaced from day one. And so so what I want to now do is say, well, that's nice and ancient. We now know that our universe is nothing like that. And by the way, if you came here to understand, to see, say, well, this guy's going to talk about the jazz, the physics, like physics is jazz. I'm not doing that. I'm using music to tell the story of physics. I'm using music to tell a story about our universe and what we know about our universe today. And that language is still viable today. That's my hope for today. But to do that, I need to provide us a little bit, some language, okay? And I gave, I don't know, maybe a couple of years ago, I gave a similar talk at Google headquarters in Mountain View. And I think they aired this to all 60,000 engineers virtually, and I'm sure only 10 people showed up. But I felt very empowered to make the following statement to all the Google engineers. I said, in this slide, I'm going to talk about the most important scientific concept. And nobody disagreed with me. So these were engineers, by the way. And I'm going to talk about it. And I'm going to break it down, okay? So as I showed you, why is it that an instrument, when I play an instrument, it generates these sequence of vibrations, okay? It doesn't generate any old thing. I play my saxophone, it is designed, unless you're John Coltrane, of course, it is designed to be digital. Right? It's just, well, I can play that game. We have a sax player here. He knows we can play this game. We can do weird things with the instrument. We could break the rules, but right? Why does it do that? Why does a vibrating body do that? So what I want to talk about is the idea called a Fourier transform. It is at the heart of pretty much every science I know about, including physics. Signal processing, it just goes on and on and on. Okay, I don't want to get into how on and on it goes. And the basic idea I want you to understand is that if you are watching waves come in an ocean, come to shore, you have all different types of waves, yes, don't you know? And there's some oceans where the waves are very smooth, right, and very regular. We call those things periodic waves, right, because those waves repeat, like that idealized picture here. And there's the idea of the Fourier transform, okay, is the following, that if I take that wave and I add it to another wave that's also repeating, they're called periodic waves, these are special kinds of waves, and I could think of them as an alphabet, A, B, C, D, where A and B and C differ because that wave is bigger and that wave is smaller, for example. That wave has more wiggles than the other wave. And in fact, we can count the number of wiggles, 1, 2, 3, 4, 5 wiggles, 3 wiggles, right? And the number of wiggles tell me how different one wave is from the other. They're similar in that they repeat themselves. So that's the language, first of all. And the idea is that, notice that if these 3 waves come crashing and they run into each other, what you end up with is probably some chaotic, more complicated looking wave, yeah? You probably see waves coming up, boom, 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 and then like, this complicated wave, right? So the idea of the Fourier transform is that simple waves can come together, they can add up together to make a complicated wave. Nice, right? But here's what's interesting. Given that the mathematics behind the Fourier transform is what's powerful about this, is that you can do the reverse. If I present to you a really complicated looking wave, this thing allows me to decompose it into simpler waves. It's like taking a complicated word and decomposing it into the letters of the alphabet. And this is at the heart of signal processing. This is how your cell phone works in these times. You get signals from outer space, it decomposes it into a signal that's meaningful to you. And this is very important, and it is actually a feature of Mother Nature. Nature does that. Your ears do that naturally. Your ears get sound waves and decomposes it into these notes. So it's kind of cool. But what does this have to do with anything? Well, it turns out that's exactly what Pythagoras discovered. That what's really going on with instruments is the patterns that are produced, these series that are naturally produced when an instrument vibrates. These things are what we call, these series of waves are what we call, another word for that is a harmonic, right? Harmonic just usually means, a repeating wave. That's just another word for, a wave that repeats. So we have the first harmonic, which was my C. The second harmonic was the octave, C sharp. I'm sorry, high C. The third harmonic was the fifth. And if you go up and you do that 12 times, you generate this. Well, what is this? Well, this is one of the most important scales. Of jazz music. So it turns out that the scales that jazz musicians actually kind of intuited, Charlie Parkins people, when naturally it was a universe, basically. Okay, that's another interesting thing. That's another conversation. So we'll get back to that. So Coltrane's intuition was not that off. All right. So there's a music theorist, a jazz pianist named George Russell, who taught at the New England Conservatory of Music, and he wrote something called the Lydian concept of jazz, and that scale is generated from the harmonic series. I see some of the jazz cats looking at me like, whoa. Okay, that's interesting. So now, I've given you one tool, which is harmonics, waves can come together. We're going to use that tool to understand something deep about the universe. Remember, I'm going to talk about cosmology. That's what I'm hoping to do. But to do that, since we're at Davidson and people here are smart and I can nerd out, you've given me permission to do that. So I'm going to do that. The other one I want to talk about is resonance. The other concept we need to talk about is resonance. So again, there's nothing deep about resonance, nothing intelligent about it, because when you were a kid and you used to play with swings, unfortunately, I didn't understand resonance too well because I fell off the swing because I should have stopped when the swing went too high. Okay, but we know that when the swing goes up and down and up and down, if you want to go higher, what do? You kick when the swing went up again, right? So when the swing went to its highest point, that's when you kicked. You didn't kick when the swing was like midway because it'll slow you down. Yeah. So resonance is when you match the frequency, you add energy into the natural oscillation of the periodic motion. What do I mean by that? If you were to look at a swing go up and down and up and down, it creates a periodic motion. So to make this wave get bigger and bigger and bigger, right, you would basically add energy to match the natural oscillation of the thing. Yes? That's called resonance. Right? Resonance is the phenomenon where if I match the natural frequency of an object, like an instrument, I will generate a larger amplitude, a larger signal, a larger sound. So we all familiar with this when we hear about opera singers breaking glass. I don't know about opera singers breaking glass, but I know about some people who sing really badly, and like I'm like it breaks my ears. But anyway, so the point is that that's resonance. You're matching the natural frequency of the glass, and so when you match that, the opera singer sings at that frequency associated with the size of the glass, and the glass breaks because the oscillation gets bigger. And this is a nice plot for those. We have some particle physicists in the audience. You know, we talk about resonance when we create and annihilate particles. It's the same phenomenon. We also have resonances in the orbits of planets, and this goes back to Kepler. You know, Pythagoras is right. These are called orbital resonance, and we use this actually. Well, not me, but my colleagues at Brown who study exoplanets use this to discover new planets. And in fact, I have a colleague, not a friend. I can't believe I'm giving love to this guy. He hated on me in my book. When my book first came out, I was so excited. My book got reviewed in the New York Times Book Review, and this guy reviewed the book. And he was an astrophysicist turned to a jazz pianist, and his name is Dan Tepfer. But actually, one of the things that Dan did do well was he actually wrote down the notes for this TRAPPIST system, and he has a nice blog entry. So you know what, Dan? I'm giving you love back, all right? All right. So now I've given you these concepts. I've given you these tools now. Now we can now talk about, we have right enough to talk about what? Remember my job here was to convince you that I was able to find some way of reconciling my physics with my cosmology and with my music. So that's what I'm doing here. The other thing now is to understand Einstein. Oh, what I should have said, and let me cool down and calm down. I get very excited sometimes. I should have taken my ADD pills, but I haven't done that in like 15 years. What I should have said is that, okay, Kepler did it. Kepler helped us understand why it is that, you know, there's some usefulness in music and understanding music to understand something about our world aside from music. But now we know that our universe is not just made up of our planets in our solar system. Our universe has tons, gazillions, I like that word, of stars and galactic systems. And why should that have anything to do with music or sound? That's what I should have said a couple of slides ago. And what I'm now going to tell you is actually it was key to a Nobel Prize in physics, the modern rendition of that. But to get to that, we need to understand something about space and time. And in a nutshell, what Albert Einstein helped us to revolutionize and understand is that space and time, or space, let's talk about space, can warp in the presence of massive objects. And the reason why, in fact, the gravitational pull of the sun on the Earth is not really a force, okay? It is a feature of the fact that the sun warps space and the Earth moves along the contours of that warp space. There are other phenomena of this warping of space that is not a force, for example. All right, so a black hole, which we find is in the middle of our galaxy, we found many more, do other things in the warping of space that's not a force, for example. So what it is, that's another conversation. All right, so that's one thing. And so one of the ways that Einstein showed, and his people after him, was that if the universe is, instead the space-time of our entire universe can warp, one way that it could warp is that it can actually warp outwards. It can expand or contract. And so this was a prediction in, you know, the early 1900s, somewhere in around 1920. And it was confirmed experimentally in the 60s. So the idea that the universe had been expanding, and so this picture is supposed to mean that there's some moment that I'm not going to talk about, called a Big Bang. Actually, I will talk about it. And as the universe expanded, it was hot and dense, okay? And as it expanded, it's cool, and all this, there's some kind of energy or plasma or something like this that we talk about. And then stars and galaxies, people and planets form later on. And you're going to say, yeah, this is sci-fi. Okay, keep going. And what I'm going to show you here is a real picture of the universe 13.8 something point something billion years ago. So why should you believe that this is a picture of light 13 billion years ago, 13, 14 billion years ago? Why should you believe that? Well, here's one way to believe this. Pick up your cell phone. How many people have friends or relatives that live very far away, like in Europe or Asia? Yeah, good. You're from Turkey, right? You know when you pick up the phone, oh no, the best is no. Call somebody that's sitting next to you. And when you call them, notice that when they're talking to you, there's a delay. That's because the light, the electromagnetic, the radiation from your phone has to go to outer space to the GPS satellites and come back. And it takes time for light to travel. Light has a finite speed. Good. So therefore, the light that we're seeing here that we've collected took 13.8 billion years to get to us. So it's that old. It's revealing a source, okay, that's that old. So this is a picture of the baby universe. And I don't see any stars or galaxies or people in this picture, okay? And if you look at this, and here's the thing that's interesting. In the 70s, in the 1970s, we didn't have this data. This data was from the early 1990s and has been since refined since 2018. It's gotten better and better and more precise. It looks completely chaotic and nonsensical. But now what we're going to do is use the tools that we talked about that's coming from Pythagoras to understand this. But before I tell you anything about understand it, we're going to understand that physics. What is the physics behind this? Here's what we're going to do here. It turns out that what this is here is, if you look at that picture, imagine that 10 billion years later, it became this. And notice what you see here. I want maybe a student to tell me what this resembles. What does this picture resemble? What do you see in here? What kind of pattern do you see? It looks like a web-like type of pattern, right? In fact, we call it a cosmic web. And actually, if you say, well, what is it? What are the nodes of this web? Well, if you zoom out, you pick a little point here, and you zoom out, what you see, what that is are clusters of galaxies. So our galaxy, like the Milky Way, belongs to a collection of billions of galaxies that originate from this. So how did the galaxies start off? Oh, let me explain what this picture is. This picture is revealing that in the early universe, again, according to our understanding, the universe is highly energetic, and all of the atoms and everything that could form atoms have completely dissolved. And it's basically what we call a plasma, a very hot plasma of energy and radiation that's basically undergoing undulations of energy. We call it the cosmic microwave background radiation. And the different colors correspond to whether the wave is higher or lower. And here's the other thing that's interesting. How high and how low is basically 1,000th of a degree. If you think in terms of temperature, it's a very tiny difference. So how do these tiny waves become these galaxies? That's the puzzle. But before we even had this data, this is data, in the 70s, there was a physicist named Jim Peebles who was working with Einstein's theory of the expanding universe and said, suppose the universe was expanding and we had this thing, we didn't have the data. If I think about this in terms of sound waves, what does that predict? And that is the rabbit hole we're going to go down. So this is real pictures of clusters of galaxies and things like that. And the way to understand this is to go back to my intro. So actually, I lied. Instruments are not perfect oscillators. What makes instruments interesting, right, is that it has a color. Your violin is different than another person's violin because your instrument has its own signature. Just like your voice is different than your voice. So when I play my instrument, in this case, I play a G. Actually, the instrument to the x-axis here, well, every point corresponds to one of those frequencies that I was telling you about. When I play an instrument, it's actually generating at the same time a whole series of vibrations, of frequencies. At the same time, is that your ear hears the one that's loudest as the note. So G will be there. But the others, your brain perceives it as the color, the timbre of the instrument. What makes an oboe sound like an oboe? What makes a flute sound like a flute, even though they're playing the same note. So these other frequencies or formants, okay, we perceive that as revealing some characteristics of the instrument, such as its shape, such as the material makeup of the instrument. And given that, we can now understand that if we now do the same thing, not for the instrument, but we treat the universe as an instrument, and we say, let's understand all these vibrations and see how many of them correspond to a given frequency. I look at the spectrum of the frequencies of the vibrations of these waves in the early universe. Is it as chaotic or senseless as what we're seeing? Because this makes no sense. The universe looks very chaotic here. And surely there must be some order to our existence, or maybe not. And what Jim Peebles did was he did that, and this is what he found. I want you to compare this to an instrument. So in an instrument, what we saw was many of these peaks. And the one up here is what we call the resonance. Remember I said, so there's something about the instrument that accepts certain frequencies because of its geometry. In this case, the shape or the size of the instrument. And then the other ones may correspond to whether or not the instrument is made up of a particular type of metal, or made up of wood, or made up of something else, or made up of goat skin if it's a drum. It's revealing the material makeup. So does the universe do the same thing? And what Jim Peebles showed was that when he took this data and put it through the lens of waves, like he did a spectrum, boom, you got a resonance. And then these other things should somehow correspond to the material makeup of the universe. And let me show you something. The red line is a theoretical prediction from Jim Peebles' calculation before there was this data, given 45 different parameters, the best fit. Okay, these 4 parameters correspond to some things that I don't want to have a long conversation. And the black line here is the data. And so now what we understand is I gave a lecture in Winnipeg, which is where Jim Peebles was born a couple of months ago. And I was so happy to pay homage to my master, Jim Peebles. This third peak here, if you go and do the calculations, okay, reveals how much dark matter is needed. 13 billion years ago in the early universe, this thing called dark matter. You need more gravity than gravity can have to make galaxies form fast enough. It turns out when you measure the amount of dark matter today in galaxies, it is bang on the same number, 14 billion years ago. All right. We can read off other contents like the number of neutrinos and visible matter in the universe, just by looking at how the universe was vibrating like an instrument. And that's why he won a Nobel Prize a couple of years ago. So the analogy of, sort of using sound to analyze not just the Pythagorean universe or the Keplerian universe, but our contemporary universe still holds. All right. And so if I have 5 more minutes, I kind of want to say some things about quantum physics. Otherwise, I'm happy to end the talk. Do I have 5 minutes? All right, good. So, I felt the basic point here, I did nothing, okay? I didn't make up any of this stuff. Other people did it before me. And it was great because it was like, okay, hey, Jim, you want to go jam at the club with me? And he goes, no, I don't want to do that. But he used, my point is, I was happy to know that we can, it's okay to use the music and the sound to talk about your physics. And I'm not the only one, right? Lots of us that do this kind of game. But then you think, okay, that's where it ends. Then I got an email years ago from this gentleman here. And if you don't know who he is, you probably know who Wynton Marsalis is and Trombone Shorty and John Baptiste and all these other people. Well, he was their mentor. He's Big Chief Donald Harrison. He's the NEA jazz master. He played with Art Blakey and Miles Davis, to name a few. And he wrote me and said, I'm interested in the intersection of quantum mechanics and jazz improvisation. And I was like, oh, that's interesting. And to make a long story short, it turned out that there really is something there. And what I want to kind of do is kind of say something about the quantum world and what that has to do with music, and especially improvisational music. What Richard Feynman taught us is that I'm not going to drop this bottle, but if I drop this bottle is going to take a unique trajectory to get from point A to point B. But what Feynman discovered, actually, to get that, right, for that to happen, what's really going on microscopically is that the quantum particles have to traverse all possible trajectories in some weird ways at the same time in order to get from point A to point B. That's what's going on in the quantum world. And I teach a class, I've been teaching it for the last couple of years, and one of the things I enjoy doing is actually deriving classical physics from this picture. So in the quantum world, real quantum things that traverse many paths at the same time to do this. And what you end up seeing is that. And what I was going to go with something here. Nope. Well, right. What I was going to show you was a slide where there should have been a slide where what jazz improvisation, one way of thinking about jazz improvisation is that instead of a particle making a trajectory, a note to go from one point to another point, if I do something like, if I go from G to D, or I can go, right? That's like Sonny Rollins, isn't it? They're all possible paths that could be taken to get from point A to point B. And what Donald convinced me of is that at every given moment, for a very advanced improviser, all of these paths are considered at the same time. So there's John Coltrane for you. I wish he was alive to know about this. And on that note, thank you for your time. I know that I kind of went over a little bit, but one of the reasons why I like doing these types of talks is that I'm kind of selfish. I like to get questions or comments. Do we have time for one or two? Okay, please. Oh, that's a great question. Haverford is very, not, especially now that I've visited Davidson, very similar to Davidson, okay? And really, really smart students, great professors, world-class professors who are also committed to teaching. One thing that I felt as a disadvantage when I went to grad school was like many of my classmates who had gone to larger universities, like were exposed to the graduate school world, and they may have taken a few graduate courses, and that did intimidate me. But I stuck around and I realized there were some advantages to going to a small liberal arts college, which was I learned how to write. I learned how to write. There were all these other skill, I don't know, skill sets or things that I was more attuned to that came into play. And that was a very good advantage. So thanks for asking that question.
How did you sort of persist in both the careers through that struggle?
Thanks. That's another great question. And I'm really pleased to see the students asking questions. That already tells you so many great things about the school. And that's another thing I have enjoyed about being at Davidson. I've gotten some really difficult questions, which is a reflection of like the depth of, the students here. But I have to remember the question that you asked. Yes, say that one more time. Yes, okay. I think we need, one of the things I realized I wasn't doing, I was doing it not without even knowing it, right? Was I kind of was an antenna. I tried to identify other outsiders like myself. And you find these people, even if they're not alive. Like I found it in Einstein, I found it in Coltrane. I was able to find other people that validated that it was okay to be me. And the wonderful thing about that is that those people are out there. The question was, who would I say is my favorite physicist? Ooh, that's a tough one. That's like asking this saxophone player who's your favorite sax player. Unless you have a favorite sax. You don't, okay. Okay, you're gonna put me around the corner. You're gonna put me on the corner here. You know I'm not gonna say Einstein. And you know I'm not gonna say Feynman, even though I like all of them, right? Well, my favorite physicist alive is Helen Quinn, because she was a mentor of mine when I was at Stanford, and she invented something called, she solved, something called a strong CP problem, but then it turned out that that solution led to the best dark matter candidate known to us. So she is my favorite physicist alive because she's also cool. And she's also very strict. Okay. Yes. It's not the axion. So it goes to show I can love the physicists and whatever, but not be down with the discovery. That's a tough question. What's yours? Wimps? Oh, I don't think it's a wimp. We talked in your class this morning that how I went to the extent of 15 dimensions and all the string theory. And then I came back down to earth. I moved back. I moved out of 10 dimensions and I moved into an apartment called 3 dimensions. Okay. And now that I live in 3 dimensions, I've become more and more of a minimalist. Can I get more for less, right? I'm in North Carolina. I want more for less. I want a deal. I want a sale. You know, if I get that pulled pork, I want it for the least amount of money. Maybe pulled pork is my dark matter candidate. I like, I think it's some kind of fermion. Okay, what type? Maybe you can help me figure it out. But I think it could be, if it's not a thing, it may be something much weirder, right? It might be something so crazy that we have not even imagined that. And which means that there's a lot of work for y'all, Davidson students, to carry on the baton while I lay back in my hammock and get fat on pulled pork. Okay? I don't know if that was a good answer. But any more questions or comments? Yes, sir.
Gave us was sort of non-traditional physics, and that at least in that one book review that you invoked, maybe there's some kind of traditionalist or orthodox physicists who push back against you. What is the essence of their critique, and how do you respond to that?
Yes, because that critique does exist. And to be frank with you all, you are this new kid on the block that comes into the sandbox and we don't play with the toys this way. Get out or whatever. You're not welcome. That's kind of the metaphor here. How do I? And my response to them is, well, I'm just following with the tradition of Albert Einstein. Because one of the things if you look at Einstein and how he worked, Einstein would never do the math first. He would come up with thought experiments. He would come up with a picture. He would come up with a way of exposing the paradox. Oh, it looks nice. Everything looks nice and normal. I'm going to find a thought experiment. I'll make a gigantic bottle in outer space, and I'm imagine a bottle in outer space and a lasso that's 1,500 light years. And then why doesn't the lasso bend? Whatever. He would come up with these thought experiments. And in a lot of ways, this is very much in the tradition of those thought experiments. And likewise, in the music side of things, you have, if you look at a lot of the jazz legends, when you really go under the hood and you talk to them, again, it's a similar thing going on there. And for me, it's not an either or, it's a both. Yeah, you should. You're here in college, for example, to learn those rules. This is very important to pick up those skill set. You will acquire that and with your, under your own agenda, but don't stop there, right? So it's not an either or, but a both. And in fact, if it's the other way, without the substance, then that can also, you can, run afoul with that too. But thanks for asking that question. Yes, sir. Oh boy, I'm getting all the hard questions here. Well, it's called Club Davidson. We're gonna, in fact, last night I played with some of the jazz, with some of the jazz cats here, and that was loads of fun. And boy, what great players they are. Let me see, my favorite jazz club, I don't know even the name of this place, but when I lived in London, there was a place in East London that was really cool. I think maybe it's called the Vortex. I'm glad I came out of it though. I like your t-shirt, by the way. Wait, it's not Chick-fil-A, it's something else. Oh, okay. I said, thanks for asking that question too. That's a great question. So the secret, actually, one of the things I didn't say here is that no matter what you do, by the way, whatever you're going to do in life, okay, end up doing, if you get it into enough you know, what ends up happening is that you might develop what you call a secret sauce, like maybe your own way of, and everyone, by the way, we all do this, by the way. We all have like our way of maybe of grokking this thing, of getting it, right? And so for me, yeah, in a lot of ways, the exercise of just trying to understand something through a different lens, and it doesn't have to be music. In fact, when I gave this talk at Google, some guy, was trying to be an a-hole. He was like, yeah, well, who's to say that I couldn't write a book about the biology of physics? Huh? And what about, I was like, actually, you could. Why don't you do it? So the idea of making these analogies is a useful exercise to maybe help you see what the object that you're looking at through traditional lens in a way that may, maybe help you do something with it. Wow. Okay. That's it. No more questions. So thank you so much. Maybe this is the first time I've done this, so I'm actually going to play something for you all. Okay? Because normally I don't do that. I just do a demonstration. I'm just going to make something up on the spot while people walk out so that, I can at least feel I earned my money. Okay. So I'm going to ask the musicians in the audience here. Okay. Okay. So F, give me something else. Not a key, but just something. Okay. This guy's getting difficult. Oh, no. Oh. Oh. It was a little bit different.